then you're just reading it. Doesn't need much too much energy on our part, except once or twice it highlights some points. But not this book.
Right, right. What got you interested in TAOCP in the first place? Did you see references to it somewhere, or how did you find out about it?
It was fluke, I should say. I did not know about TAOCP till
Okay,
I saw your this one. What
okay,
happened was I was trying to see if there's any study group for. There's another book called the Pragmatic Programmer.
okay.
I think there are some famous books, right? Like 10 books which people recommend to read.
I see.
The Pragmatic Programmer,
Okay,
Clean Code, Clean Coder. So I was
right.
trying to see if I can get any study group for any of them. And in
Mm-hmm.
Meetup, the only study group which popped up was yours.
Okay, cool.
And
That's
then I
great.
thought, okay, let me see what it is. And then I tried to find out about it.
Okay.
And then that's how I joined the third session. I thought second I was not prepared. Third I joined, and then I tried to watch. I tried to read about Don Knuth to see what
Uh-huh.
he does and what it is, and that's how I came in. I should say.
Okay, great. Great. I think let's just go ahead and begin. And if people
Okay.
join, then they can join in the middle. Otherwise, we will just continue on.
Okay.
So here's a little question. What's your preference? Do you like, coming up with solutions that are sort of high level, or do you like working at the lower level?
I think it's mix of both. I think
Hmm.
I don't know. My background is DevOps, so you see the high level how to change in the high level infrastructure, and also you have to go fix in the. I don't know your context of this question.
Okay. So you don't particularly prefer or enjoy one over the other.
Yeah. Um,
Okay, cool. So today, as I posted the agenda, we're like towards the end of that initial introduction to MMIX. Um, and so, we've covered sort of the basic instructions, the arithmetic instructions, and
are you
um,
going to record now, or did you start recording again? Sorry.
I am recording right now. Yeah.
Okay.
And so the the instructions that we've covered were like very straightforward, right? That you could load data from memory into registers, or you
Mm.
could store data from registers into memory, and then you can perform some kind of operations on the registers and
Mm.
change the data. Um, but the instructions that we will cover today will allow you to affect the control flow of the instructions, because normally instructions are executed one after another, and so with the jumps and branches, that's what would form the basis of being able to write conditionals and while loops, things like that that affect the control flow of the program. So that's the idea, and then afterwards we can do some exercises. Um, and since you've been here, right, you know the procedure, but
Mm.
we'll
Yeah.
just try to follow that same procedure as much as possible. And again, because it is being recorded, it's something that I want to go through. And when people watch the recording, then they can also um, find it useful.
Yeah.
So uh, Knuth had this to say in one of his books on MMIX, and I think it kind of goes back to what you were talking about from his the videos that you saw. That what was his goal with designing MMIX in the first place, and then deciding to use it for his book. And so he really wanted something that would have kind of a balance between being able to be picked up or learned relatively easily. He wanted it to be simple and elegant, but he didn't want to necessarily sacrifice complexities either. So he didn't want it to be like just for learning or just so simple that you couldn't actually use it in practice. So he did both. And so I think it is important to keep that in mind when we're learning about the instructions and the design, that this is not simply just for learning. Like he's really meant it to be usable with a real computer that would be built. So far, I don't think a computer actually has been built using MMIX,
Mm,
but it's still out there, so it could happen.
yeah.
So yeah, so we'll be reading this section, start
Okay.
with this immediate constants on page 13. So we can read till about 2:30. Okay, what do you think?
I think a lot of concepts. Um, don't know.
So, did you follow the difference between how you would use a constant in an instruction instead of a register?
It says that it, one thing they say is from 0 to address FFF, it has the numbers saved as constants, these numbers.
Is that the
Third paragraph in the
third
page
paragraph on page
14.
14?
Yeah. Is that what it means? Several instructions feature wide immediate constants.
Okay, so right. So what he's saying here is that if you remember, one instruction has four pieces to it.
Mm.
There's the opcode,
Yeah.
or the name of the instruction, and then there's the first operand, which is usually the destination register,
Destination, yeah.
then the second operand, and then the third operand, which are usually like the input
Mm.
registers, right?
Yeah.
So each of these four pieces is 1 byte.
Yeah.
So that means that
Four bytes.
8 bits,
Total.
right? So 1 byte is 8 bits,
8 bits, yeah.
right? And so what that means is that you can have a value from 0 to 255. If you wanted to use that 1 byte position
Mm.
for something else, maybe not an integer, maybe not a register number, you can use it as a constant number.
You
So
can
for
use it as a
example,
constant number. What? Okay.
right, so let me write that in the chat. So let's say that we had add, and we were going to put the result of adding register 2 and register 3 into register 1. So we would have something like this.
Mm. Okay, yeah. It's the 2 and 3 content is added and put in one.
It's put in one, exactly. So what he's saying is that if you didn't want to necessarily use a register for one of the numbers that you want to add,
Mm.
and if the number is if it can be represented by 1 byte,
Mm.
then you don't have to use a register. So let's say that we were adding two numbers, and register 2 had the value 100,
Mm.
and register 3 had the value 25, right? So then instead of saying add $1, comma $2, comma $3, I can say this. I can just add 25
Directly.
directly
Oh, I see. I
to
got it. Yeah. Yeah.
register 2. So that's what he's
Oh,
saying. So
dollar.
you can
Oh, $2 plus 25.
$2 plus
Like that.
25. So
Okay.
it's sort of a convenience, right? Because otherwise,
Mm. Yeah.
where is the value going to come into register 3? You'd have to get it from somewhere, right? You'd have to
Yeah.
somehow set that value in register 3,
Okay.
which
Okay.
is
I
some
got it. Yeah.
extra work that you have to do. And he's saying that, well, since we already have a byte there, and if the number that you want to add fits in a byte, then just use it as a byte.
Mm.
That's what he's saying. So the
Yeah. Yeah.
thing
I
that,
got it now. Yeah. What
oh,
it means.
right.
Yeah.
So the thing that you're asking about is he takes
Mm.
this idea that you can use 1 byte, you can use a one, you can use a
1 byte.
constant
Yeah.
in one of those slots, and he's saying there are some instructions that will let you do this with two positions. So the instructions that he's given. So for example, this, let's look at the first one that he mentions, which is set high,
Mm.
right? So
Yeah.
set high, let's say dollar $1, $2, $3.
Oh, so if you want to put the value YZ, you can directly write the value and you can use 2 bytes. Whatever the
Exactly.
number can fit in, you
Yeah,
can directly, you don't have to use a register, just type in the number which will fit, maximum number which will fit in 2 bytes, and you can directly assign it
that's
to
exactly
X.
what it is.
Okay.
That's exactly what it is. But he
Yeah.
doesn't let you do that with every instruction. So for example, you can't do this with add, but you can do it
Yeah.
with these, the set
Set.
and the increment and the ORs. So you can do it with these instructions. And did you see why he allows it with these instructions at the end of page
Oh,
14?
I didn't reach. Yeah, I didn't reach till there.
Oh,
It's
okay.
just stuck in the,
Okay,
yeah.
so
Just a
we can
minute,
just
yeah.
look at it right now. So, he has that list of instructions, and then he
Yeah.
says using at most 4 of these instructions, we can
Yeah.
get any desired octobyte into a register without loading anything from memory.
Yeah.
So, that example that he's given,
So,
do you want to go ahead and maybe explain that?
so he's basically telling we can, whatever number I need, I can put it in the zeroth location directly. Like if I want to load set, so I'm actually, uh, so $0, I'm trying to set a value. Um, increment. Comma hash 0123 is a comment, right? No, it is hash was something else.
No, the
Hash.
hash or the pound sign is for hex. So it's
Oh, the hex
zero,
number. So
yeah,
it's
so it's
directly
zero, one, two,
loading
three
the,
hex, because he says that you can use 2 bytes together for the
yeah.
set instruction if you wanted to. That's why he has those 4 hex values, because 4 hex values are 2 bytes, right? Four
Yeah.
hex
Yeah, yeah, yeah.
digits
4 hex is 2 bytes. Yeah.
is
Yeah.
2 bytes. So
Yeah.
so that's what he's saying, that the first. So
Oh,
his
so
point
01 and
now,
2, 3.
right? Go
Okay.
ahead.
So 01 and 2, 3, they're hex values. You can directly, they are the hex. They represented here in hex format, and that directly gets loaded into $0.
Yeah.
You don't have to do anything
So let's
else.
write
It
that
just
out.
directly gets loaded.
Yeah, so
I
let's
see.
write that out. If I have
Yeah.
this one, right, that's the first
Hmm.
instruction that he's given. So can you type in what's in $0 after this instruction? What's $0?
0123.
Yeah, can you just type it in, because then we'll continue with the
Yeah.
remaining.
Yeah. So um, $0. Should I say what has um, hash?
Yeah, that's exactly right. After this instruction, the second instruction is the increment. So then he says increment
He increments
medium
it
high
by 4567.
$0.
Is it that what it means? Whatever you have it in $0, you increment it with 4567
Okay, so
hash.
your turn now.
Is
So
that
can
it?
you type in what's in $0 after this increment instruction?
I don't know how the addition of. Okay, should I try addition? It will be like I need to do 0123 hex plus 4567. Instead of 7, 8, 9, 10 is A, like that. A, then 6, 7, 8. 1 second. It will be A, 6, 7, 8, 5, 6, 4. 4689. 468A.
Okay, actually, I realized that we made a mistake. We
Okay.
made a mistake after the first instruction. So after the first instruction, it's not strictly that. Let me type in what it is actually. So
Mm.
it's 3, that's 2, 2, 3, 4, 5. So it's this. After the first instruction, it's actually that. Because the first
Mm.
instruction was set high, um, set
Yeah.
high,
That high wide.
set high wide, right? Set high wide. So do I have that right? So 1, 2, so 0, 1, 2, 3 is the highest um, wide, the highest 2 bytes. So then I have
Oh,
6
after
bytes
that you have,
remaining to the right, right? So if I've
yeah,
typed it incorrectly, I should have 1, 2, 3, 4, 5, 6 0 bytes.
yeah. You
So
know, if you see in the page where the first example is set high, page 13, the first example of set high $x comma yz,
yeah,
set high wide. Here they do whatever is in yz is stored in x, and it's multiplied by 2 power 48.
yes, because that's exactly what it is. Um, 2 to the 48 in terms of bytes,
Yeah,
because 1 byte is 8 bits.
68. Yeah,
So
2
48
power.
divided by 8 gives you 6 bytes.
Mm,
So it means you've shifted whatever that value is 6 bytes to the left. And when you shift it 6 bytes to the left, what is left are just zeros in those 6 bytes.
oh, that's right. Okay, that's right. That's okay.
That's just a mathematical way of saying
Mm.
that he wants to set the highest 2 bytes to a particular value.
Yeah, yeah, got it. Yeah, now got it. Yeah,
And that's why the name
takes
of
a
the
while. Yeah.
instruction is set high wide,
2, 6. Yeah. So
right?
0, 1, 2, 3. Yeah, yes, you're right. 0, 1, 2, 3, and then 6. 1, 2, 3, 4, 5, 6. Yeah, you have 6 zeros after that. So you have more. Oh, each zero is represented by 2. Okay.
Right, because
You have 8
each
zeros.
zero is
Yeah,
one hex digit.
yeah.
And so one hex digit is 4 bits. So 1 byte, you need 2 hex digits. And that's why I've separated out each byte that way.
And
Okay,
then the
so
increment. Increment
yeah, so
is
that
different then.
then he does
Yeah.
the increment. So now can you type in what $0 will have after the increment? And
0, 1.
this is not just
Yeah.
increment, right? This is
Yeah.
increment medium high.
Medium high. Oh, okay. Medium high is increased by medium y. Uh,
So medium, if you look at the definition of medium high,
yeah.
he's multiplying it by 2 to the 32, which
Medium high is
means,
2
yeah,
to
32
32 or 2
divided by
to
8 will tell you how many bytes.
2 to 32 it says here. Okay. So it's going to be the center 2. It will be like the next 2 bits because we took 0, 1, 2, 3. Then we'll take 4, 5, 6, 7.
Okay, do you want to type it out?
Yeah. So this is increment MH. We'll have 0, 1, 2, 3 we already have. Then it will be 4, 5, 6, 7, and 1, 2, 1, 2, 1, 2, 1, 2.
Perfect. That's exactly right.
Mm.
And so you can see that because it was shifted 4 bytes to the left, the low 4 bytes are still 0.
Yeah.
So that's what he means by medium high is, you call them the center bytes, but there's two centers in that sense.
Mm.
There's the center that's towards the higher end, and there's the center that's towards the lower end. So that's why the name of this instruction is increment medium high. So, sorry, not medium. Is it medium or middle? It's
Yeah, it is
medium.
medium.
Yeah, medium. Okay,
Medium high.
medium high. Okay, and so then the next instruction is increment.
Increment L.
Okay, I'm going to
L is
type out
low.
the instruction and you can
Increment
think about
L
what
is
it will mean.
medium low. Or increment ML is medium low is the center byte. It will be the third center, like I don't know how to type it.
Yeah. Can you type
It will
out
be,
what's in
yeah,
$0 after this one?
it will be INCML or $0 value to center. So 0123 is the high. When we say high white, this is the one, right? 0123 is high white. 4567 is the medium high, and then this is whole. Okay, this is half done, right? Is it half done? No, not half.
This is medium low.
Yeah, this is medium low. Increment medium low, and then you have 89AB. Medium low is what? Medium low is 2 power 16. So this is from the right side now. It will be after this 8, 9, A, B, and then we will be left with 1, 2, 1, 2.
Yeah, that looks right. That's absolutely right.
Medium low.
Because you were going to take 89AB and we're going to shift it 2 bytes, and that will set the center to, but to the low end.
Oh, so we have only two, high and medium. So extreme right
In the
will
middle.
be the,
Yeah, in
yeah,
the
yeah.
medium,
It's
right? So
just
for medium, you have high, which is towards the left, and low, which is towards the right.
right. And the
Okay.
medium is the high medium is the second four, and the medium low is the second last four bytes.
Yep, that's right. And so then finally, we have this instruction.
Increment low. The low is the last one.
Yeah.
Yeah. Okay. This was good. Yeah, same thing by last four registers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E. Yeah.
Yeah,
Oh,
there
this
you
is
go.
good.
There you go. So that's sort of the idea that with these, how many instructions does he have here? Like 4 sets and then 4 increments, 4 ORs and 4. So these 16 instructions, you can get any value directly into a register without having to load any data.
Mm.
So that's the benefit of these instructions. And then at the end of page 14, he says that um, for set low, you don't have to write set low. You can just say set.
Okay.
So if you just see
Mm.
set without the actual
Yeah, I
position,
see the last line. Yes.
yeah. So then it's set low. So that's sort of like if you just said set a register to 1, then
Mm.
it means it's setting the low byte
Okay.
to 1, the rightmost byte to 1.
Okay.
And then the other thing that he says is that if you just say set um, of 2 registers, it's basically setting one register to the value of the other register. So if you don't use 3 operands, if you just use 2 operands, then that's sort of like an assignment of
Okay.
one register
Got
to
it.
another
Got it.
register. So those are the two things. Uh, Okay, so let's move on to. Do you feel pretty comfortable with these
Yes,
instructions?
I think, yeah. Today,
Okay,
I think I feel much
great.
comfortable looking at it
Yeah,
seriously.
that's exactly what it is. Because it's so different from high level programming languages. The syntax is so different. If you just try out a few examples, you get a really
Yeah.
good feel for it. Okay, so this section, it has a little more stuff. So let's spend about 7 minutes till about 2:57. We'll
Okay.
discuss that. Okay.
Yeah. So this page 15 had one was relative address, jump to a relative address. Another one was a go, which is absolute address.
Yep, that's right.
Jump and branch. This was true for jump. Jumps two possible ways. And then branch. Branch is a conditional jump. Yeah. Branch is a conditional jump, and they, for all of the branching, they have used relative address only because of the restriction of number of bytes available.
That's absolutely right. Yeah.
Mm, sorry, I didn't get this starting one. The tetrabyte is 4 bytes, 4 bytes, right?
That's right.
And the way he converted this one, I didn't understand the way they converted the line. For example, jump at plus 4. This is in second paragraph,
Mm-hmm.
third line. At plus 4 star 2, symbolic form for tetrabyte F 6 zeros and 2. 6 7 and 2 6 1, 6 zeros and 2. I didn't understand how this is translating. 4 into 2. Jump.
Yeah. What he means by the symbolic form is every instruction has the instruction mnemonic or the name, right?
Mm.
So, for example, jump is the name of this instruction, but it also has an opcode. Remember, I think
Okay. Yeah, yeah.
you had noticed like the differences in the numbers for each instruction name. So jump has the opcode. If you look at this, I would say that the opcode for jump is F0.
Oh, okay. Okay.
That's what he's saying, that the
Oh,
tetrabyte,
okay.
because each instruction is 4 bytes.
Yeah.
So that's all he's saying, that this instruction, when you write it out in English, it looks like this: jump at plus 4 times 2. But in terms of the symbols or the numbers or the bytes, it's actually that 4 bytes. It's F0 for the opcode, and then 00 for the first operand, and 00
Mm,
for the second operand, and 02 for the third operand.
yeah. Okay. F0 is jump. Okay, that's what he said. Jump forward. Uh, and then, so it is just when they say jump at plus 4 star asterisk 2. This is just the 2 here. It's written here, right?
It's the two
Is
that
that
he's
how?
written in the instruction.
Oh,
Yeah,
okay.
it's exactly that. But do
Okay.
you see that he's actually, if you look
It's
at
a
the
look.
symbolic form, okay, so let me type out the symbolic form here in the, so symbolic form is found F 0, 0, 0, 0, 0, 0, 2, right?
Yeah.
That's the symbolic form. So the first byte we know, that's going to be jump, right?
Yeah.
That's pretty clear.
Yeah.
Okay. Uh, how does the remaining 3 bytes, how do they represent what he's written as the operand? The operand here, operand, uh, operand is
Yeah. 4 into 2 here.
at plus 4 times 2,
8, which is uh,
right? That's what he's saying. The operand, this is the operand.
yeah.
But
I
in
see like I mean, mm,
Yeah,
hexa
but
is
in symbolic
at.
form, we just see the 2. So where's the at and the plus 4 and the times,
Yeah.
right? That's sort of the question. Like in the assembly language, you have all these other things, but in the machine code, we only see the 2. And the answer is that's fixed. So if you write a 2,
Yeah.
um,
That's a constant you're saying?
yeah, so the at plus 4 times 2 is always going to happen with a jump. That's what he's saying.
Oh,
So he's
because
saying this is the relative address. And if you look at the first sentence of that paragraph,
yeah.
where he says
So,
which could be written more explicitly as at plus 4 times xyz. So he's saying that xyz are the three operands, and they will be always be used this way. You're going to at is the current location, is the current address. And so the jump instruction will always take the current address and it will add 4 times whatever the XYZ is. And here,
okay.
XYZ is 2,
2.
right? Because the other 2 bytes are 0.
Yeah.
Byte X is 0, byte Y is 0, and only Z is 2. So
Mm.
XYZ is 2.
That part I understood. Hash 1000 to hash 1008. They're just making it jump 8 uh, because of 4 into 2. 8. This is 8 and you make it jump. No.
Yep. Yeah. So he's saying, uh, in the example, he's saying that at is
Yeah.
pound 1,000,000. Yeah, 1,000,000. So in the example, he's
Yeah.
got at to be that address, hex 1000.
Mm.
And so then he says, if you
Jump.
if you have that instruction where the XYZ is just 2,
Mm.
then the next address is going to be um, next address.
Yeah, he wants to jump by 8. That's why he says they wrote it like that. Instead of writing jump hash 1008, because it's not necessary. 1000 is the add location.
Yeah, that's the calculation that that instruction is making.
Okay.
Right? Because at is hex 1000, then you do a plus 4 times whatever the
Mm,
XYZ is 2, so
2.
you get hex 1008.
Yeah, I think remaining is all the similar way. He gives example of minus later with F1, second
Um,
paragraph.
yeah, so if you wanted to jump backwards,
Yeah.
then you could give a negative um, XYZ.
Yeah.
That's what it is.
Yeah.
And
It's a two's complementary.
yeah, the two's complement of whatever that number is. And yeah, so then you have the ability now to jump forward and to jump backward. And but I think that the difficult part here, when I first read it, was really understanding what he means by a relative address. Like what is that expression that is allowed as a relative address? And so, you can have these sort of formulas in there in the instruction that are going to use at, and then, you can have some other stuff in there as well. So in that second paragraph,
Yeah.
where he's saying you can say jump at minus 4 times 2, and then it will figure out like what is that supposed to be.
Yeah.
So jump at 4
Okay.
plus
Yeah,
2,
yeah.
jump at minus 4 times 2, so that's jump backward. And
F1 and then it was all
right.
minuses.
And then uh, for Go, he says that you can jump to an absolute address. Why do you think he needs a separate instruction? Like why is there a jump and why is there a go?
One is relative, but in programming wise, when you go from one location to another, um, I can think of functions which are getting called, but they are maybe for globals or constants they use go. No, that's not a change.
Yeah, I think that you have the right intuition. Basically, with if you look at jump, right? Jump
Yeah,
can only take a relative address because what he means by relative is that it will use the current address and then it will either add or subtract some other value from that current address,
yeah,
right? And so
yeah.
what's the maximum that it could change the current address by? The maximum it could change it by is
67
three
million
bytes,
by
right? Three,
3. Okay,
whatever three
yeah.
bytes can represent.
Yeah.
But 3 bytes is not enough to go anywhere in memory because memory
I
is
see.
actually
Yeah,
64 bits. That's
yeah, yeah,
8
yeah.
bytes,
That's the
right?
reason.
So,
Yeah.
so if you were thinking of any like arbitrary address in memory, that's just some 8-byte value. And if you're at some point and you want to go to anywhere in memory, but you're only allowed to add or subtract 3 bytes, you can imagine that that's not going to be enough.
Yeah, yeah, yeah.
So
Yeah,
that's what,
yeah.
right. So that's why he has the go instruction, because with go, you don't give it a relative address, you give it actual registers, and those registers have 8-byte values that you can, you know, um,
Generate and save it beforehand so you
yeah,
can jump.
exactly. So you can put those 8-byte values together to come up with some final 8-byte value that you can go to. So that's also
Mm.
like a jump, but it allows you the entire range of memory, whereas
Yeah,
jump limits you. It's based on your current address, like wherever the current instruction is, you can go, maximum this far back or maximum this far ahead.
yeah. I see. Yeah, 67 million, or here it is 2 for 18 for
Yeah,
the.
yeah.
Is that
So
for the goal?
so that's the basic difference. So if you wanted to um, just go somewhere nearby, like if you're at some current location and you wanted to have some other instruction executed that's not the next one, and it's not too far away, like maybe it's some function, right? There's some function
Yeah,
call, and it's maybe, in that same module, then maybe it's not that far away. And so then you can use a jump. But if it's like a completely different location that's somewhere really far away in memory, then jump may not have the ability to go to that address, and so then you would need a go. That's
the
the
syntax also. The syntax is like go x y z. Is it to fill up all the uh, y and z? Is they're usually 2 bytes, right? They are not 4 bytes. The
um,
syntax for go
mhm.
dollar $x comma dollar $y comma dollar $z.
Yeah,
So
yeah,
to save the fill in the address, we are using y and z. Y and z is usually 2 bytes, right? Each is 2 bytes. There should be 4 bytes.
No, why each of X, Y, and Z is 1 byte.
They're 1 byte?
Because every
Okay, cool.
instruction has 4 bytes. The first byte
Okay.
is being taken up by the instruction name or
Okay.
the opcode, and then each of the operands can be 1 byte.
Okay.
And 1
So,
byte means that you can have 256 values. Now, normally in most instructions, that 1 byte is the number of a register. You know, there's 256 registers.
yeah, yeah.
So normally when you have some value in one of these operands, that's used as a register number. And then what we do is we go to that register, we look at what's inside the register. What's inside the register is 8 bytes.
Okay, got it.
And then we can use that value from inside the register. So
Inside, okay.
that's the difference between Go and jump, that Go is not using that single byte as the value itself. It's
Yeah.
using it as a register number.
Register.
And then, because it's a register number, so then it can contain like the full range of all the
Yeah.
addresses. So that's sort of the main difference here. Another interesting thing that he
So it
says
still
about,
comes to almost accessing 8 byte plus 8 byte only, right? X is still used to store. Is X is also used? No. X is used to save the address.
yeah, yeah.
X is
So,
also used because
right.
you're
So
going to jump
exactly.
directly. Okay.
Yeah. So what does X get? X gets the current address plus 4, which will be the next instruction.
Okay. That's why it's plus 4.
And do you see the explanation at the end of that paragraph?
Um, yeah, therefore we could return that one, you mean to say?
Yeah.
Return to that location later by saying, for example, go $x, comma $x, 0.
Yeah.
And that is the register. No, sorry, I didn't understand this before.
Okay. Let's say that the address, let's say that $x, let's use a specific register. Let's say $1. Okay. So
Okay.
$1 is, let's use that value that he used before, 1,000 and just 1,000, just 1,000, right? So this was
Yeah.
the example that he had for jump,
Yeah.
that the current address is hex 1,000. So when we say go $1, comma $1, comma 0, what is this going to do?
$1 and 0, they both have the $1 has the addresses, so that is 8 by $1.
$1 holds 8 bytes, but I've given you the value above, right? I'm saying we're going to use $1. We're going to assume that $1
Oh,
has that,
1000. Okay.
has
Yeah,
hex
you already gave
1000
me
inside
the,
it.
yeah.
Yeah,
Yeah, you gave me hex 1000 and
yeah.
the value next one is 0. Uh,
So that's a
so I'm,
constant. So that's a
yeah, that's a
constant.
constant.
Okay. So when
So
we add it, what do we get?
we jump to the 1000 address.
Yeah, we jump to 1000. And then
No,
what
sorry,
happens
my
to,
question was, are we saving the first $1 after go? Are we saving it in it, or are we using it to
we're doing both.
access?
We're
Oh, we're
doing
doing
both.
both.
So we're using it and saving it.
Okay, that was my question. Okay, I
And
understand.
but what is saved is not hex 1000. What is saved? Like after this instruction, what does $1?
+4. Yeah,
Yeah.
it will be
So
+4.
so $1 becomes 1004.
Oh,
Right?
yeah. They say therefore we could return to that location later by saying, for example, go $x$0 with z as 0 as an invariant constant. This is how we can go back to the place where it was called from.
Yep. Yeah, that's exactly right. Because we know that whatever our it doesn't take you back exactly to that address. It takes you back to the next address. It takes you to the next instruction. What's saved is not, you know, whatever $1 was. It's whatever um, you've calculated as the new $1 plus 4.
Now, I still didn't understand how you go back. Like if I moved already,
Hmm.
the content, so you can see $1's contents was 1000.
Yeah.
So I finished 1004, and then I will still retain the value of $1. So I go back to $1. Is that what you mean?
Um, I think I may have confused both of us. I think what I wanted to say was this, that the current location is 1000 because that what he used earlier in the previous paragraph was the current location, not the value in the register. So this is the current location, hex
Okay.
1000, right? So we're at some instruction and that instruction has address 1000, right? So
Yeah.
then what he's saying is that let's take register 1, okay? Let's say that
Yeah.
register 1 has the value hex 1, 2, 3, 4. Okay, so if I would summarize this, I would say currently we're at address 1000. We want to go to 1, 2, 3, 4.
Yeah.
So then I say go $1, comma $1, comma 0. So then what does the current address become? It becomes 1,
1, 2,
2,
3,
3, 4.
8. Add it. You have to add 4.
No, no.
Okay.
The current address becomes whatever that calculation was. Because you see in the definition of Go,
Yeah.
he
At.
says at is assigned the address. The address is the sum of $1 and the constant 0.
Okay. So that is 1000. 1, 2, 3, 4 here.
Yeah, 1, 2, 3, 4, because that was $1. So
Yeah.
now what's interesting is that after the instruction, what is $1? That's sort of the question.
Mm.
After you have gone to this new address, 1, 2, 3, 4, what does $1 become after this instruction? And if you look at the definition of,
$X. It is in $X. It's a fixed register, is it? No, it is in $1 here. It says before going to the specified address, the location of the instruction that would ordinarily have come next is placed into register $X.
Yeah.
So the next instruction, before we move, before it is going jumping to the address of
Before it is going.
$1.
So
It saves it.
can you type in what is $1 going to be?
So it says before going. What is $1 will be #1234.
No. 1234 is
The current location.
at will become 1234 because that's where we've gone. So after the go, we've already gone to 1234.
So whatever is
But
the
what's in
$1 should
$1?
have is
What's
the
in $1?
next instruction. So whatever was the next instruction,
Which
address.
is, remember, every instruction is 4 bytes, right? So
Yeah,
it's going to be 4 plus where we were before.
4 plus where we were before. Yeah.
So what is
One,
$1 going to be?
1238.
No, where we were before the instruction. Before the instruction ran.
Add was 1000. So
Yeah,
1004.
yeah.
Okay. I got it.
So can you type that in?
Yeah, 1000.
So $1
Yeah.
after the go.
This is saved in $1, right?
This is saved in $1. Yeah.
Yeah.
So what does it become?
1000.
No, 1000
It is
is,
next one, 4. 1004.
yes. So yes, this gets saved into $1. So do you see what happened? With
Yeah.
Go, you can go anywhere in memory, right?
Yeah.
But once you've
Yeah.
gone somewhere, if you wanted to return where you came from, that old address has to be saved somewhere. So it's
Yeah.
using that same register that you used in the
Before you
Go.
jump, you save it. If not jump, before you go to the address, you have to save
Yeah,
it in this
right,
register. Yeah, that
right.
is.
If you wanted to return, then you
Yeah.
would care about this, and so it's always there, right? So that you don't have to save anything. This is what Go does. So
Yeah. Okay.
this is like Go will do this for you. So it will always save the address of where the Go was, and it'll add 4 to it because obviously you don't want to go back to the Go because that's sort of this infinite loop, right? If you
Yeah.
came back
Yeah.
to
Yeah.
exactly
Yeah.
Go,
That's
then
different.
you would
Yeah.
jump again and you would come
Yeah.
back
Yeah.
again.
Yeah.
So you actually want to go back to the next instruction. Think of like a function call, right? So you
Yeah.
have a function call and then you return from a function call. You don't want to call the function again. You want to go on to the next line, right? It's that kind of reasoning.
Yeah.
So this way, you can go to anywhere in memory, but if you wanted to return, which you normally do, you can always do that because your old address, at least the address right after, or the address of the instruction right after, is being saved,
Yeah. Yeah.
right?
Yes.
Um, okay, so yeah, it's way past 3. Did you? Let's take a break.
Okay.
And I was thinking, since nobody else is here, what we can do is instead of continuing with the sections, I can do the visual debugger. Did you attend one of the sessions with the
Yeah,
debugger?
I've attended all your visual debuggers.
Okay,
Yeah.
so we can
Yeah.
do the debugger and we can try out these instructions in there. And we can,
Yeah.
actually see, like, we can just try out any different values and see what happens.
Yeah.
Does that
Because
sound
that
good?
debugger is not available for Mac. It's only on Windows. That
Isn't
particular
it? I
debugger.
thought the web page said that it
Yeah,
is
I
available
can
for
write
Mac.
programs in Mac and run it, but not that particular visual debugger. It's not available for Mac.
But the web page says it's available for Mac.
No, you can write MMX programs and execute it, but it has probably the regular debugger, maybe the command line one, but not the one you had displayed.
Oh, okay.
Yeah, that particular one. If you go to that page, the one where you downloaded, you
Yeah.
would notice it's only exe is there, .exe.
Oh, okay. That's too bad. Um, are you not able to run Windows programs?
No, I don't have Windows one.
What about, there's a way you can run Windows programs on Mac. What is it called?
I don't know if I have a Docker and then I can get any free
Oh
Windows.
yeah, definitely with Docker, but I thought that there was also another software that lets you run
Yeah, I've heard about it. I think
Parallels.
yeah,
Parallels.
Parallels. Yeah, yeah.
Is Parallels free or do you have
No, no,
to?
I don't think Parallels is free.
Oh, I
I
see.
think I have. Yeah, I remember somebody using it. I don't think it is free. And Docker, I had a doubt that maybe the it may not give us the free images for Windows.
Yeah, you're
Uh,
right about
they're
that.
usually paid ones.
That's right. That's right. You won't be
Like
able to get.
Linux and everything else is free, but that's why I did not attempt the Docker.
What
I'm very
about,
familiar.
can you run Linux?
Yeah, I have access to CentOS. Yeah.
Okay, so maybe, let's see, MMIX
Mm, let's
Visual
see how it is.
Debugger. That's really weird because I thought that the web page said, so if you go to the web page,
Yeah. It's
um, let
it's
me
called Visual
actually,
Debugger. Yeah.
let me share this so we can see this,
MMIX VD. Yeah, that's the page. Yeah, this
right?
one,
This
right?
one.
Yeah. You can
So
see it says on the top it's a .exe. You see it? Yeah, this.
no, no, on the left side in the navigation, this area
Yeah.
here. So this one, I'm going to click on the Mac OS. So here you're saying the Visual Debugger is not available.
Yeah, you can write the program. I think I downloaded the source code also. I think, and I can run the MMX program. I can, but it doesn't have the visual debugger.
Oh, I
Yeah,
see.
yeah, that was good one. The visual debugger because it shows you how it's changing the values of
Yeah, yeah.
registry. Yeah,
Let me see. What about Linux? So same thing for Linux. It doesn't
yeah,
have.
it doesn't have. It's only the um, Windows.
Oh, okay. So that is not good. What would you do?
The other one I can try write. I can write program. I think I downloaded hello.world. I think MMX. I think it's from
Yeah, but it's not
not.
as nice to use because it's
You
not
don't
that
see.
easy
Yeah,
to see all the registers and the memory
yeah.
and the entire file. So I was just wondering like what we could do. Yeah, so I guess we'd have to somehow build it for Mac or Linux, and then I guess the question is the UI available? Probably not, right? Because the UI on the Windows executable, it looked very Windows specific to
Yes,
me.
it is. Yeah.
Yeah, so I have a feeling that maybe for Mac it's not, the UI is not available for Mac. Oh, okay. Um, we can still try it. I mean, if you want, I'll just screen share and
Yeah, no, I think today you're going to do some demo, right? I'll try to see how I can do
yeah,
something for Windows to see it
okay,
because that probably helped a lot because you get familiar to see the code and it
right,
just
right,
feels
right.
easier.
Okay, so let's take a 10-minute break and then we can spend
Yeah,
like 15, 20 minutes on the
yeah,
demo.
yeah,
And then that should be good enough.
yeah,
How does that sound?
yeah, yeah, great.
Okay,
Thank you.
great. See you.
Yeah.
Hey,
Hi, I'm back.
so Michael just joined us.
Oh,
Hey,
nice.
Michael.
It's a good time. Debugger is interesting.
Michael, do you hear me?
I hear you.
All right, cool. Um, yeah, so we had covered. I don't know if you looked at the agenda, but let me just show you that slide again. So this is what we had intended to do, but since only Deepa showed up earlier,
Yeah.
we
You
just
know
went
what?
through things a
You
little
know.
slowly. Yeah, go ahead.
You know what? The, I had I tried to come last week, and on the meetup page, on the link that came with it goes to the meetup page, and it says event happening now, and it's grayed out. I couldn't join, and I
Really?
thought, yeah, I thought maybe something had happened where maybe I tried to RSVP and say that I'd joined last week, and maybe it didn't take, and it wouldn't let you in if you didn't take it, if you didn't RSVP. And so I made sure that I was RSVP'd for this one. Now, this one I had to be late because I had another engagement. I didn't even think I'd be able to come in. I guess it's over, huh?
No, no, it's not. It's not at all over. I mean, we covered some of the sections,
Yeah.
but yeah. So I'm just like, what
Same
exactly
thing happened
did you
again this
see?
time, though. Same thing happened again. When I followed the link, it said event is happening now, and it was grayed out. I couldn't click it. I don't even know how I got in. I went back, and it looked like it was asking me to RSVP again, and I clicked it. I clicked attend now, and then the link was there. It's instead of saying link is visible to attendees, it had the link, and I could click that. Something weird is happening. I don't know what it is. Um,
If I
I think
understand you correctly, do you think it was a Meetup issue or was it a Google Meet issue?
it was definitely a meetup issue.
It's definitely a Meetup issue.
Because I wasn't when I clicked the link in the email, it took me to the meetup page, not to the Google page, but to the meetup page.
Okay.
But the meetup page that described the event, TAOCP number 6,
Yeah.
and at the bottom it said, in the right hand corner, it said link will be visible to attendees. It
Yeah.
didn't have a link.
Oh, that
And
makes me
then
feel so
at the
bad. That
bottom it says,
I just feel so bad. Like people may have been
yeah,
trying
I
to
think
get in and
maybe I'm not the. I mean, I was thinking it was my problem last week. I was thinking
oh my God.
maybe I didn't get the RSVP and it's not allowing me in. And I was thinking, well, geez, they should let anybody in on something like this, whether or
Well,
not they RSVP. Maybe
yeah,
Meetup
what
will want that.
yeah, one of the mistakes I guess I made was that previously for the first three or four meetups, I used to send this reminder email
Yeah,
with some other information in it. But then I figured, I'm not really adding anything that the meetup page doesn't already have. So
except the link.
I I just kind of assume that, people will be able to get through via the meetup page. But if that's not happening, anyway, I'm going to post a comment and I'll email everybody who was signed up but didn't show up that, possibly you were denied or you couldn't get in. So yeah, I'm really just I feel so bad because I can imagine, I have attended meetups in the past, and if a couple of times what has happened is that the meetup was full, like when we used to have physical meetups, right? You show up
Right.
at that door, you spend 15 20 minutes on the subway and then whatever, and then you show up at the door and they say, oh no, the meetup is full, I'm sorry, you can't get in. And I used to feel so frustrated. um, that's really I feel so bad. Anyway, we will definitely make sure that there's a link available for the next time and you can always get through. And I'll also provide some more direct way of contacting me. So then, you can always if there's any issue. But
That
anyway,
means until you RSVP, it doesn't show the link, right? That's how Meetup has set up. If you do not
but Michael is
RSVP,
saying that he had RSVP.
no, he said, I think from his conversation, I felt if you don't select that you're going to attend, looks like it doesn't show up the link, even though you have joined the group.
Okay.
No, not joining the group. You have to RSVP, which I did.
Yeah.
Yeah,
And right now, if I go onto the event page in Meetup, it says you're going, and then at the bottom where it has that link, it says happening now. But that does it's grayed out. I can't go anywhere. But right now, when I go on there, it has the link up in the upper right hand corner,
Okay. But and you were able to use
or
it,
the
and then
box in the right, the
you
box in
got
the
in.
upper right hand side.
Yeah.
Yeah, I don't know why I don't know, but even today, when I first sat down, where it says online event, it said link will be shown to attendees, even though it was me who was logged into Meetup and I had registered.
Yeah.
And then there's another place at the bottom, it says, it has the link and it says, right now it says you're going. And where it says join the event, it's a red button. Usually it says happening now and it's grayed out. You can't click it. So I
Yeah.
guess you can't click that one at the bottom unless if you're late.
Right. Right. Which is a
I
shame,
have
right?
I
Because
have joined late in the past, maybe 10 minutes
hmm.
or so late, and I was able to join. That's why I have a doubt whether it is because I'm
Oh,
joining late or we have to RSVP.
okay.
That's my question.
Well, no
Oh,
worries. I mean, you're here now, and I was just sort of recapping what we had done earlier before the break, which was look at and read the two sections on using constants and the jump and the branch instructions. So, Michael, if you want to go ahead and open up those sections, I was going to do a demo in the Visual Debugger and share that. And the idea was that I don't have a demo prepared for this one because I wasn't anticipating to do one. But the idea is that we're just going to try out things. So
okay.
we'll just make up some data. We'll try out instructions, and so feel free to suggest anything that you want. And so let me go ahead and share this. Okay, so that's the debugger. Let me just fix the size so it becomes a little bigger. I was able to get it a lot bigger than it. Okay, I think I need to type something in first because it's hard to tell.
I
So,
think it's fine.
okay, so let me. All right, so now we at least have. Okay, how does that look?
It looks fine.
All right, cool. So the two sections that we've covered were the immediate constants and the jump and branch sections. So let's go over the immediate constants first because that's pretty useful. Um, so if you remember, the every program has to start with a instruction that has the label main. So we'll do that. We'll we'll give it main. And Deepa, do you want to go ahead and give us an example for the immediate constants? What can we try out? Should we try out the examples that we tried before?
I think so, yeah. Whatever
Okay.
we had. Yeah.
So that's on. Let's do the example that he showed in
Page 13. Page
which
14.
page is it? Page 13.
Yeah. Page 13 starts and the examples are on page 14.
Example is on page 14, right? So this is the example from page 14. So let me put a comment here. Okay, so there we have, Michael, do you see the towards the, it's the fourth line from the end, from the bottom of page 14.
Yeah, I'm with you.
All right, cool. So if you look at this, what he's saying is that certain instructions can use constants instead of registers. And because each register or each operand is 1 byte, the maximum values that you can use for those constants are from 0 through 255, essentially, right? But there are certain other instructions, like these set instructions and increment and or and add. These can actually use 2 bytes as the constant. So you get a wider range for constant values if you want to use them. This example that he's given is showing how you can use a combination of these instructions to get any value into a register. So you don't have to load the number or the value from memory. In your program, you can just generate that value and put it into a register. So that's what he's showing over here. So if we do this, and then we run this, save it, make this a little bigger. Okay, so close this. And so now you can see in $0, this instruction has not run yet, so I need to run this. So let me step over it. And okay, so do you see the 0, 1, 2, 3 in the high byte of $0 over here?
I think, yeah. 0, 1, 2, 3, and then all are zeros.
Right? So what set high does is it sets the high byte. So I'm going to so that's what happened. Okay, and then the next thing is we want to increment medium high. $0.4567. Okay, I have to rerun the program every time I make a change. So we just ran the first instruction. Now the second instruction, do you see what happened? Because we incremented what was there already, what happened was that $0 $0 became 0, 1, 2, 3. That's what happened. We
A
incremented.
double question. Why do we also see $1 register here? Just it's a garbage value, the $1, the right side. No.
We see $1. Oh, I'm sorry. I shouldn't use $0 and $1 because remember $0 is argc and $1 is
Oh,
argv. So it's actually better if I use $2 and not use $1. So then I won't be affecting that. So let me go ahead and change that and run this again. Yeah, so now I've got the value in $2. And the reason why $0 and $1 are non-zero are because it's saving the command line that I had set for some other program that I had run before. So in the options menu, in the run menu, there's a command line that you can give it. And I was running a program before that was doing some of the matrix instructions. And so I had given it this command line, matrix, and then I'd given a hex string. So it had three arguments. And that's why $0 is showing up as 3. So what I'm going to do is I'm going to erase this because for this particular program, we don't want any command line. So the next time around, you'll see zeros in there. So, but anyway, we'll stick with $2. And then the next thing that we want to do is we want to increment the medium low 2 bytes. So that'll be increment medium low $2, comma pound 89 AB. Okay, step 1, step 2, and step 3. What do you think, Michael?
Yeah, it's simple enough.
Okay, so and then we'll do the final instruction, which is an increment of the low 2 bytes. And that gives us CDEF. Save it and run it again. And then, so this way, using some combination of these 4 instructions, we can set a register to any value. We don't need to actually load data from memory. That's sort of the point of these instructions. So then we moved on to the next section on page 15, which is jumps and branches. So we want to play around with jumps and branches. So let's first try, Deepa, what do you want to try first? You want to try a jump or a go? Oh, I guess Deepa dropped out. So Michael, did you get a chance to read about jumps and branches?
Yeah, I read about that before.
Okay,
I mean, I
so
obviously joined, but
okay, so let's try jump. Okay, so let's try a jump here between these two. Let me put a jump here, right? And so at is the current instruction. And so if I say at +4, that's just the next instruction. So
that doesn't do anything.
it
Really.
wouldn't change anything compared to before. Do you want to try this out, or just to make sure that that's the case?
Go ahead.
Okay, let's try it out. So save this, run it again. And okay, so now same thing. Okay, so no problem there. What if we change this to at +8? So then save it, run it again. And here. So we skipped the increment of the medium low. And so we have those zeros in between. But we did run the increment low, so you do get the CDEF. What if we put a jump here? Let's say we wanted to fill in that hole where the zeros are with the 89AB. So then what could I do here? What's the relative address I can give here so that line 13 is run?
You do at -8.
At
Is it?
-8. Okay, so let's try that. -8. Save it. Run it again.
Yeah.
And okay, so we got the CDEF in there, and now the jump, and now we've got increment medium low of 89AB. So we filled that in. Of course, now we've got an infinite loop because next time around, okay, this just added another CDEF to the low bytes, but now we're going to go back to line 13 and we're stuck in an infinite loop because of that jump. So that's what a jump is. It takes this relative address expression and There's various kinds of things that you can do in that relative address expression, but this is a common thing that you would add or subtract something from the current address. The other thing is the you can do a go. So let me comment this out. And let's do a go. But with go, you have to give it an absolute address. And the absolute address is calculated from registers. So we could just use like the fact that $0 is 0, like there's a 0 in register 0. So if we just give it an offset that is one of these instructions, one of our previous instructions, then we should be able to just go there directly. You see what I'm saying?
Yep.
Okay, so what I'm going to do is Go takes a destination address, destination register as well. And if you remember, in the destination register, what gets stored is the current address plus 4, which is sort of the next one. So let's use $3 as the destination register, and let's use $0 as the base address, and then let's go back to the second instruction, maybe line 9.
So that would be immediate 4.
Immediate 4. So I'll just say 4 here.
Yeah.
So let's do that, save this, and then run this again.
I learned assembly language on a CDC. This act of putting the next address into a register was the way you didn't have a stack on CDC.
Okay.
What you had was I don't remember what it was called, jump subroutine, I think it was called. But jump subroutine, you didn't have a return. What happened is you got the address of the next instruction after the jump call in one of the registers, and then you could jump. There was a jump call that jumped to that the address in that register. That was how you return. And if you wanted to make a recursive subroutine, you really couldn't do it that way. You had to manage your own stack. This is ages ago. This was a CDC 6500 with the 60-bit words.
So I see a lot of similarities in what you're describing and the purpose or one of the common uses of the go instruction here, because that's a topic that we haven't covered yet, and I was thinking of saving it for a little later. It's the topic of subroutines, and the way Knuth says that you can do subroutines in MMIX, he provides 3 or 4 different ways that you can.
MMIX doesn't have a call, does it?
MMIX doesn't have a right. It doesn't have a call instruction. That's what you mean?
Yeah, it's like it's a lot more like the CDC than I thought.
Yeah. It doesn't have an explicit call instruction. So
it doesn't have an explicit stack either. So there's no such thing as pushing.
It does actually. So that's one of the instructions that we will cover later. So there is this concept of a register stack. But what Knuth describes in the text is that's not the only way that you can go to a function. So he says that there's 3 or 4 different ways. And one of them is the register stack. And there's a push and jump instruction that lets you do that, use the register stack. And we'll go into that a bit more next time, not next time, but when we cover subroutines, which may be like a few meetups away. But that's the idea. But it sounds like you are at least familiar with one way of doing a call or a linkage of a function or subroutine. And that's exactly what this is. So,
it's
yep.
different. It's different than a Z80 or an Intel where you have a stack pointer, and you don't get the address of the next instruction in any register when you do a call. There's a call instruction, and the call instruction puts that address that wherever the stack pointer points to, and then a return instruction which moves the stack pointer up and sets the value at the top of the stack to the next instruction. And then you can also push data, like if you're doing a subroutine, it'll have arguments, so you want to make a stack frame. I know how to do that on a Z80. I'm less familiar with how to do it on this way. I guess you just have to set it up like a stack pointer and a base pointer has to be done.
I think you'll find this really interesting when we actually do cover that topic, because all of these things that you're describing, those are also available. So there is a push J, and then there's a return as well. We just haven't covered that yet.
Yeah, but there's no stack pointer. So where does it push it to?
So there is this, yeah, so there is a register stack that it takes care of for you when you use those instructions. So there's a certain register that will hold a return address, and then you can say return. And so there in MMIX, it's not the only way. So you have a choice of doing something much more primitive and simple if you don't want to do that. But what you're describing in terms of having the argument saved in registers and then those registers available to you in the called subroutine, that is there. But it gets a little complicated. So so that's the idea. But yeah, so it sounds like, yeah, definitely you know this from experience, and you can see a lot of the parallels here when you look at the MMIX sort of take on these things. But should we run through this program and see what happens with the Go?
Yeah, okay, go ahead.
Okay, so let's do that. Let me save this and run it again. Okay, so now when I run this, we did the set, and now we did the increment of the medium high. Then we do the jump that puts the C, D, E, F in there, and then we do the go. So with the go, as you said, $0, which is 0 plus 4, will get us back to line 9. But what we should also look at is what happens to $3, because $3 is going to be updated so that we can return back to the go, or at least the instruction after the go. There is no instruction right now, but so see what happens with $3. So you see, $3 became hex 18, which is really the address of the instruction after the go, because the address of go is hex 14. So go brought you back here on to line 9, which if I run that, we should have another increment of the medium high. So $2 changed, but you can see that $3 has this address of the instruction after the go. So this way you can use go to go somewhere, and then in your destination register that you used for the go instruction, you have that place where you came from saved. And so if you wanted to go back, you could do that using that.
That's it.
Yeah. Yeah. So that's the go. And the jump is the relative address. The branches, all of them use the same relative address format. So you can say, branch negative or branch 0, and then it will check the register. So all of the branches take one register and a relative address. So the register is what is checked for the condition, whether it's negative or 0 or positive. And then the relative address is something like, at +4, or it can be even more complicated. But that's the idea. Then, you would have the the conditional branches. And so if you just wanted to do an unconditional branch, that's jump. You've got the conditional branches, and then the go, which allows you to jump to any arbitrary address, because a relative address has that limitation. Since it can only use 2 bytes, there's a maximum offset, forward or backward that you can go to. So if you need to go somewhere really far away, then you would have to use go. Okay. Sound good?
Sounds good to me.
All right. So I guess we'll call it a day for today, and hopefully we can resolve any joining issues for next time.
Yeah, I was surprised I wasn't able to join. Another thing too, I was wondering because I looked on the YouTube list, and I because I missed last week.
Mm-hmm.
I wanted to see the replay, and it wasn't there. So I thought, oh, maybe this is
Yeah, that's my fault. I wasn't able to review the
recorded.
video because I'd like to create the outline. So then, you can go to various places in the video. I just haven't had time to do that. But I did post the chat. But yeah, I'll update the comments.
Yeah, I eventually found the chat.
Yeah, yeah.
I only found the
So,
chat this morning though, because I
okay.
didn't.
Yeah, I'm sorry about that. I was just a little behind on posting the video, but I'll make sure that this video gets posted in the next couple of days along with last week, so then at least people won't have any confusion about that. All right, thanks, Michael.
Okay, great, thanks.
Yeah, see you. Bye.
How do I get out of this?
I'm sick.